to the other course, 102. So here we come finally to something, I hope at least also for you, something really interesting, and that's some glimpses towards Fourier analysis. So Fourier analysis goes back to one of the classical great people, Fourier, who studied some modeling problems and found out that actually you can understand the functions, which in biology are called signals, and he was working in the engineering way, dealing with signals, and understanding the signals can be achieved by understanding some combination, superposition of simpler functions, which we do understand and are periodic, and the frequencies are what build then the whole thing, together with the amplitudes of the individual signals. And it goes back, for example, to audio or other kind of modeling and handling of data. We shall of course start from scratch, and we shall not see the impact so easily, and we shall start with talking again about spaces of functions. And this is a point where the point of view of the vector spaces and norms there and distances, etc., merge with the flow of the infinitesimal analysis, and we shall see it immediately. So as usual, the first thing we have to do is to pick up some reasonable space of functions we want to work with. So we are still working in the realm of analysis of one real variable. So our variable x, or whatever we call it, will be in an interval a/b. It could be bounded or unbounded, that's not the point. And for sake of simplicity, we shall deal with functions which are good enough for most of the applications, at least as soon as you discretize things, definitely yes, except of the stochastic behavior and the very wiggly things which would appear in say the Ito calculus and similar things, modeling, say stock market evaluation or things like that. So we shall deal with functions which will be nearly continuous. We shall call them piecewise continuous. And what do I mean by that? It's quite simple. I mean functions. So here I've got the a and b, and I allow the functions to have some jumps in some points, but the jumps will be in such a way that they will be continuous otherwise, and there will be the one side limits there. So there will be one possible value here if we come from the left, and one possible value here if we come from the right, and the same on the boundary, right? So we want to have the one side limit and the boundaries. So we can imagine that at the points of jumps, the function has something like two different values, one from being on the left, one being from being on the right, but otherwise it's continuous. So having this in mind, the jumps are of course always finite, and therefore most of the nice properties of the continuous functions hold true as again, right? So each continuous function will be bounded on the bounded interval. It will achieve its maxima and minima and things like that, right? So this is good. And sometimes we shall need the same to go further for the higher derivatives. So this is continuity, which is piecewise, and we shall do the same with the differentiability, which will be again piecewise, and we shall say that the function is S1 if the first derivatives, well, if it's in S0 and the first derivatives are existing as well as things in S0. So they will exist except of some finite number of points where the jumps could be or changes, and there we request that the one-sided limits again exist. So just to imagine a thing like that, so for example we could deal with something like the absolute value function, right? So the absolute value function would look like this. And you see it will be very nice, and it will have, and we can make it into a zigzag function like that, right, on a finite interval. And the derivative will exist everywhere except of these bad points. But in these points, there will be one-sided limits of the derivative, because the derivative is always +1 from the left here all the way, and then -1 going further, right? So this is what will be meant by being in the calligraphic SK. So in particular, just having told that the S0 are behaving nearly like the continuous ones, it's clear that all functions in S0 are Riemann integrable, and they are Riemann integrable even in the absolute value, right? Because it's only finite number of subintervals. We can split it to them, and the function will be continuous on each of them, and we can integrate. So that's easy. And now we shall talk about how different our functions are. Again, yeah, so that's a crucial point in every data analysis, to decide whether two objects are close or far away. And for time being, we shall introduce two distances. One of them will be the so-called L1 distance, and it's defined this way, right? So it's the Riemann integral of the absolute value of the difference, and we take it pointwise. So you can imagine it's like taking the distance on the real line via the absolute value. Our functions might be complex valued, or actually could be also valued in some Euclidean vector space. Everything would be the same, and the absolute value has got the same properties all the time, so we need the triangular property inequality there. So you see, the only difference is that if two of such functions have got distance 0, it not necessarily means that they are equal, which is somehow seems strange, right? But here they are equal up to the finite number of points where they might be jumping. And as you know, in a Riemann integral, we can change the value of the function in a finite number of points without affecting the integral at all. So we shall just live with that. If the functions f and g were continuous, then obviously having the distance 0 would mean that they are equal. And also, if one of those functions is taken to be 0, then we talk about the norm of the remaining one. So that's the L1 norm. And of course, the triangle inequality for the scalars, so for the values of f and g, say that the same will hold true for the norms. So that's what we get. That's very good. That's what we need. And then there will be the L2 distance, and there we define it in a similar way, but you see it's just copying the Euclidean distance now. In the Euclidean spaces, we just took the differences of the coordinates, took square of them, summed it up, and then took the square root to get something which behaves like a norm, right? And here we do the same pointwise and integrate. Instead of summing finite number of coordinates, we have infinite number of coordinates for every x1. And we integrate it, right? So that's the L2 norm, and it's absolutely obvious that it really comes from a scalar product, because we can define the scalar product also pointwise the same way as with the Euclideans, with the unitary spaces. Expect the f to be complex, we shall need it anyhow. So then you multiply the first argument value with the second argument value, but conjugate it with the bar over g, right? And taking this, we get again, for functions which are in S0, that will be always existing as a Riemann integral, and we see that the L2 norm is then obtained as the square of the L2 norm is the scalar product of f with itself, right? So that's good. And obviously we can use now all the properties of unitary spaces, which we discussed in last but 1 week or how long back. And we see that in particular it has got all the properties, right? So it's linear in the first argument, it's the conjugate value if we swap the arguments, and it's real bilinear, complex linear only in the first argument, and we call it sesquilinear in the second argument if it's up to the conjugation. Right, so that's that's the message about the L2 and L1 distances in our space of functions. So that's very good. And you see, maybe I should draw the picture, or one more picture for that. So imagine we have got the function f and the function g on an interval a and b. We look at them, and of course what we compute as the L1 norm will be the area of this. What we compute as the L2 norm is more complicated, right? So you get all the differences in absolute value squared, and then you integrate, and then so if the distances are small, you add less, because if they are less than 1, then without the square it's smaller, right? And so on. So this is what we have to expect, right? So this is the computation of the distances. Right, so now we come to the important point, because as we now already know, on the whole space of functions, so this big S0, if the interval was unbounded, then we simply would restrict our attention to functions with compact support, right? And we would write S0C for compact support, and everything would work exactly the same way. So S0C for a bounded interval is the same as S0, because there everything has got compact support, right? So we can now say that once we've got the scalar product, I will better show it again, this one, this is the scalar product, then of course we can just use the scalar product as we did in the other course, right? So that's absolutely no problem. And on top of that, as soon as we deal only with a handful of functions, so they always span only a finite dimensional subspace. So we have to expect that approximating anything, and in the data analysis, in the discretized versions run through the computer, you always approximate something with only finite number of objects, right? Then you have to expect that everything will hold true, what we know, and it's nearly true, right? So let's have a look. So the first thing to look at is if I have a subspace, so how to find something similar as the orthonormal basis. So let's start with the orthogonal one, and of course there is the Gram-Schmidt orthogonalization procedure. You might look up if you don't remember, but it's run in such a way that I wish to get from the system of functions I get from you or from someone, I wish to get a new system of functions, so that always the first k ones for each k in the system, they would generate the same subspace, vector subspace, as the original one, and on top of that they would have the property that mutually they are orthogonal, so the scalar product is 0. And only, well, if I add the other condition that it's 1 if I is j, so the norm, L2 norm of the individual members of the system should be 1, then we call it orthonormal system. In general it's orthogonal, right? There would be some other positive scalar here, real. And the Gram-Schmidt orthogonalization procedure works in such a way that assume we have achieved already the first L of those, and then we compute the next one by taking the L plus first in the original system and adding linear combination of the previous ones, and we just request that the GL plus 1 is orthogonal to all the previous ones, right? And that because those are orthogonal to each other, so this gives you explicit formula for the coefficients here. So that's very easy. Here you can just see a very simple application. So we start with a system of 3 polynomial. So the simplest polynomial mappings, right? So let's have a look what it is. So I just take 3 functions. One of them will be constant 1. One of them will be x. So there's always 1. And the third one will be the x squared, right? So that's x squared, x, and 1. Right, and now we want to say, well, so we think that for some strange reason our data should be well approximated by a linear combination of those 3. How to compute the coefficients for that? So first of all, just to make it easier, we just change these generators of our subspace of 3, of dimension 3, right? 3 functions give you a linear subspace of dimension 3 because they are independent. So the first one is kept, the second one you compute just via this formula, and you see it's again kept the same, but the third one is already changed, right? And taking these 3 functions will provide us with an orthogonal system, and then we can continue, right? So we can continue. So this would be an orthonormal system, and we can go to infinity. So for each powers of x, we would just get the polynomials so that it will be and it's essential, I didn't tell it, but it's essential that we have to fix the interval, right? If you compute the same thing on a different interval, say 0, 2 or -15 plus 37, then the coefficients and the results would be completely different, but it would be always just sums. So 1 would remain 1 because, well, no, 1 would just rescale to be orthonormal, right? That's to divide by the length of the interval. Then G2 would change. It would be a combination of x and some constant, and the square would be just a polynomial with two free parameters there, which we have to compute. And this system of polynomials, which are mutually orthogonal, is called Legendre polynomials, and they are very important in numerical analysis. So in general, we can go on. So we can say that we have simply some orthogonal system of function, right? So it means that it's a countable sequence of functions. They are linearly independent over reals, and we say they are orthogonal if they are mutually orthogonal to each other via the L2 scalar product, and if moreover they are rescaled so that the individual norms of all of them is 1, then we call it orthonormal system, right? And then of course the main question is what we can achieve with such an approximation, right? So assume we take all the polynomials, and we saw that with polynomials we can interpolate, right? So if you have a polynomial of order k plus k minus 1, so we can interpolate the values in k points. But this is a different thing. We do not want to interpolate exact values. We want rather to approximate in the L2 norm, which is again usually much more wise, because the measured values you want to interpolate are usually hit by some noise. So just hitting them exactly enforces your function to wiggle. Whereas if you just approximate it from a pool of reasonable functions you expect from knowing the quality of or the qualitative behavior of your data, how it should look like, then you simply might find out that it's much better to take some approximation from your pre-designed functions, and actually this approximation might be even better than the measurement, right? And that's part of what the people call cleaning or smoothing or filtering the data, etc. So that's very important. And in general it means just to know how well you can approximate some real data, some real function, is you simply admit that the finite approximations with always looking at the finite number of them, and we know how this works from the finite dimensional vector spaces, can go on up to infinity. And then you will face such a gadget, right? So a series of functions, and that's the main reason why we talked about series of functions, because they are really popping up and useful in many situations. And now the problem is how to recognize, if you fix your orthogonal system, how to recognize what is the space of functions you may really hit by taking the power series, and also what are the conditions on the coefficients, etc., to know that the series will be convergent, and whether this is convergent pointwise or it's convergent in the L2 norm, and so on and so on. So this is what we shall do in the next presentation. So thanks for attention for this one.